Okay, in the last lecture we have covered up till the confidence interval. Okay, how to calculate it for a normal distribution, and move on towards the calculation of the sample size, which is related to the calculation of confidence interval. So in the concept of confidence interval, what we are saying was that if you are looking for the mean, okay, then 1.96 e plus minus from the mean will give you 95% confidence interval, means you will cover 95% of the population. And if you replace 1.96 with 3, then you will cover 99.7% of the population. So this is the tolerance which I'm allowing the data to go from the mean, to deviate from the mean. Okay, so this becomes my tolerance level. Okay, either it could be 1.96 e if I'm going for 95% data, or it could be 99.7% e, which if I'm going for 90. It could be 3 times e if I'm going for 99.7% of the data. So what I have is this one. So I'm denoting my tolerance level as this small e. Okay, so a small e is 1.96 e for 95% and 3 times e for 99.7%. And e we know is s upon root of n. So I'm trying to find out n here, number of samples. Okay, so I need to rearrange the equation. So I will put n on one side and e will come on this side. And since n is root, under root, so I have to do the square of the whole thing. So this becomes the final equation. Okay, so it was actually e equals 1.96 s upon root of n. Okay, and then I drive it for n, it becomes this. Okay, and if I use this equation, which is for 99.7%, and then I drive it for n, then it becomes this one. Okay, so 3.84 is the square of 1.96 and 9 is the square of 3, and why did we do the square? Because n was under root. So these are the equations we have for the sample size. Now for example, we take this question in which we have to calculate the number of speeds, and we have to be accurate within plus minus 1, so it becomes my tolerance level, and with 95% confidence, and then we can change the tolerance to 0.5 and the confidence interval to 99.7. So let us see what will happen if we have these results. So I need this table over here. Okay, so I have the tolerance level 1 and 0.5, and I have the confidence level 95% and 99.7%. Okay, so in case of 95%, I'll be using this equation. In case of 99.7%, I'll be using this equation. Now the one thing which is missing in this question is a standard deviation. So they say that if the standard deviation is not given, then an appropriate value for standard deviation of spot speed is 5. So I can take standard deviation as 5. It's an assumption. If you have the data, then we will not assume, and then we should use the value which we have. Okay, so using these values, these are the results I am getting. Okay, so these are the results I'm getting, and you can see if I decrease the tolerance level, the number of samples are more, because less tolerance means more precision, and you need to take more data. And similarly, if I'm going from 95 to 99.7%, the number of samples increase. Again, why? Because we are increasing the population we are covering. You want to cover more data, you need more samples. It's as simple as that. Okay, another thing which we do is the before and after studies with the spot speed, and we have called these studies earlier with different names such as follow-up studies or observance studies, but the purpose is same. You made some change on the road, and then you want to see the effect of that change on the traffic. In this case, we are talking about the effect of speed. So there's the data before and there's the data after. Okay, for both these data sets, we need to meet two assumptions. The first assumption is that the data should follow normal distribution. We already discussed it, that the real world data should follow normal distribution. Okay, and the second assumption is that you should have at least 30 samples in each case. So this is a common assumption for normal distribution data. Less than 30 samples are not acceptable. So in the previous example, the number of samples which we were calculating, if any value was less than 30, we will not take it. We will go at least up to 30. Okay, and this also means that those values which the formula is giving you for sample size, these are all minimum values. So you cannot go below them, but you can go above them. So if the formula gives you 20 and going 30 is no problem. But if you go 15, then that means you are not maintaining the tolerance level. Remember, we have a tolerance level and the confidence level. So if I, for example, in this case, if I go 90, then 90 means that the tolerance level will be higher than 1 and the confidence level will be lower than 95%. Okay, so if you don't take up to these much values, you take less than them, then the limits which you have set for calculating these values will not be met. Okay, coming back to the discussion of before and after studies. So in both cases, we should have at least 30 samples. We are trying to answer two important questions here in before and after studies. The first question is there a significant change in the data? Okay, so the before data has a mean of 48, the after data has a mean of 47.9. It's almost the same. So we need to ask the first question, that do we have a significant change in the data? For that, we do a test which is called as a Z test or Z test. And again, let me remind you, Z means standard normal distribution. That means standard normal distribution. But so we have a test named after it, because that we will be using the table for standard normal distribution. So how do you calculate the Z value? We have standard deviation, the before and after. We combine them into calculating SY. Okay, so S1 means standard deviation of the before sample, N1 means number of values for the before sample, S2 are the values for the after sample. So after you calculate SY, you put in the Z equation. X1 bar is the mean of the before sample, X2 bar is the mean of the after sample, and SY comes from this equation. So this is how you calculate the Z value. Now once you calculate the Z value, we'll go to the Z table. So this is the Z table. These values in statistical terms are called as probabilities. Okay, probabilities. In simple terms, these are cumulative frequencies. Okay, cumulative frequency, a more common term, but the statistical term for these values is probabilities. So how do we read this table? So for example, my Z value is 2.66. So for the Z value, the first two digits will be taken from the first column. So I will take it from here, 2.6. The last digit will be taken from the top row, 0.06. So 2.66, 2.6 from here, 0.06 from the top. So my probability is 0.9961. Okay. Now I have to check this probability against my range. What is my range? 0.95. Okay. So you find out the Z value, go to the table, find out what is the probability of Z value. If that probability is 0.95 or more, then we have a significant change between the two data sets, before and after. If it is less than 0.95, the change is not significant. We are almost in the same condition as we were before. Okay, so this is how we use it. Now second question was that if you have a significant change, did you achieve the desired value or not? Okay, so we wanted to make some change and we have a desired value in our mind as well. The change should be this much. Okay, so let us apply an example and see how we can sort out these questions. Okay, so first of all, this is a before and after study. You have the means are given, the standard deviation is given, and the number of samples are given. Okay, so first of all, we'll calculate Z value. For Z value, I need the let me put it over there. Okay, so we need to calculate the SY value and the Z value. So now everything is given. There's nothing which is to be which is not given. Okay, for the SY, both the standard deviations are given, number of samples are given. Okay, so my SY comes out to be 1.05. Okay, then I put this SY with the mean values for the Z value. Okay, this is x1 bar, this is x2 bar, and this is my sy. So now I'll calculate z from here, and my zd value, just for the sake of it, let's make it zd value is 2.19 miles per hour. Okay, now I'll go to the table and find out if it is significant or not. So 2.1 is here, and 0.09 is the last column. Okay, so 2.1 and 0.09. So my probability is 0.98. Okay, which is more than 0.95, so this means the change is significant. Okay, so we have a significant change. Probability p-value is 0.9857. Okay, so the change is significant. Now, the second thing which we need to check is, did we achieve the required value? Now they were looking to achieve a value of 60 miles per hour. Okay, from this change, whatever change they made. So they were looking to achieve a value of 60 miles per hour. Now, did we achieve 60 miles per hour? For that, we will calculate the confidence interval. Okay, so confidence interval. Now, for more practical purposes, we use 95% confidence interval. So how do we calculate 95% confidence interval? We take the mean. Okay, so I'm doing it for after data because I'm trying to achieve the required value after the change. Okay, so I will take the after value 63 mean. Okay, then I need to do 1.96 plus minus 1.96 e. Okay, I am talking about this thing. Okay, so first I will calculate the e value. Let me calculate the e value first. So e is s upon root of n. So s is 6 divided by square root of n, which is 60. Okay, so this comes out to be 0.77. Okay, then I will calculate the 95% confidence interval, which is 63 plus minus 1.96 into 0.77, and this comes out to be 61.5 and 64.5. Okay, so you can see here the required value is not within the confidence interval. Okay, so that means the 60 value is not achieved. So there's a significant change which we proved from the z value. A significant change is not up to the required value, which we proved from the confidence interval. Now why we are making these changes? Because it's a sample. Okay, so before and after the study we collected 2 samples, so we didn't have the complete data, we just have samples of the data. So looking at the sample, you cannot make conclusions about the whole population without proving it. So this is our proof. Okay, so whenever you have few values and you're trying to make a conclusion or results, or you're trying to prove results for a large population, then you have to do some tests. So these are our tests. Okay, the first test was for the significance of change. The second test is to the achievement of the required value. Okay, so the first test was satisfied, but the second test is not satisfied. So there is a significant change, but that change is not up to my required value. Okay. Then we have a chi-square test, which is used for checking if the data follows normal distribution. Let me remind you, earlier we said that the data follows normal distribution if you achieve this type of a shape. It's a smooth shape, bell-shaped curve, and so on and so forth. But this is a very vague proof. It's a very vague evidence. Okay, because anybody can make a curve, okay, and say that it's very close to the bell shape. Okay, it looks like a bell shape. So it's very vague and it is subjective. Okay, it may look bell shaped to me or close to bell shape, but some other person may disagree with me. So I need a numeric value. Okay, I need to prove it quantitatively, like I did with the Z test. So there's the exact number. If I achieve that number, I am satisfied. If I don't achieve, then I will move on. So we need something like this for the normal distribution as well. So we do the chi-square test. Okay, in the chi-square test, when you see this is the equation, you see the summation over here, because if you remember, the speed data was divided into groups. Okay, so we calculate the chi-square value for each group and then we do the summation for all the groups. What do we have in the test? N and F values. The whole equation has N and F values. N is the number of values you have in each group which were observed. So N is what we have observed for each group. How many cars were in each group. And F is called the theoretical frequency. How many cars should have been in each group. Okay, so N is actual and F is theoretical. N is what we have and F is what we should have. Okay, before we do the chi-square test, we have to perform some calculation because N values, as I already mentioned, are coming from the data, but F values are not available with the data. Okay, the data which is coming from the field. So to calculate F value, I have to do some calculations with the data. Before I do the calculations, I have to arrange the data. Okay, as I already mentioned, this is the data which we have already, this is the spot speed data, and this is the same data which we have used in the first example of this lecture. The first example of this chapter had the same data, and why I'm saying this, because we will be using mean and standard deviation of this data which we already calculated. So when I'm using it, don't worry that from where they are coming, they have been already calculated. Okay, you go back to the previous slides, you will see its calculations. Okay, so what do we do with the data? First of all, you arrange the data in descending order. So highest speed goes at the top and the lowest speed goes at the bottom. Okay, the first thing you do is arrange in descending order. Highest speed at the top, lowest speed at the bottom. Okay, which you can see over here. Then you see the highest value is infinity and the lowest value is minus infinity. So whatever highest and lowest values you have, you remove them and you put infinity and minus infinity respectively. Okay, the third change is that any groups at the start or at the end, at the top or at the bottom of the speed table which have zero values, they should be removed. Any groups which have zero values at the top of the table or the bottom of the table, they should be removed. So if I have a group here which has zero values, I will remove that group and start with the next one. Okay, and put the highest value of that group as infinity. Similarly, if I have a group of 0 here with 0 values, I will remove it and start with the group which was before that and put the lower value as minus infinity. So and if any group has 0 values within the table, we don't mind, we will keep it for now. Okay, any group which has 0 values within the table, we will keep it for now. Okay, then so we rearrange the data. It has 3 steps. First step is put in the descending order. Second step is put the highest value infinity, lowest value minus infinity, and the third step is any 0 groups you remove them, and if you remove them, then the group which you have now, any group with 0 values at the top or bottom should be removed, and if you remove them, then the infinity will shift to the next group. Okay, then the next thing is for every group I will calculate its z value. How to calculate the z value? This is the equation for converting any value to its z. In the equation I have x, the value to be converted. I have mu, the mean of the values. I have sigma, standard deviation of the values. For this data, as I already mentioned, this is coming from the previous example, so the mean and standard deviation is already calculated. If it is not calculated, we have to calculate. Okay, so x will be replaced by the upper limit of each group. So for each group, I'll put a new x value, which will be its upper limit. So we'll start from 64. So 64 will be x. Then mu will be 48.2 and sigma will be 6.14. Okay, so this is how you get 2.57 here, and so on and so forth. Every time you will just replace the upper limit because the other two values, mean and standard deviation, they don't change for the entire data set. Okay, now you see the first value is infinity. Why it is infinity? Because the first value of upper limit is infinity. Okay, and who put it? We put it, if you remember. I told you have to do this for preparing the data. So this infinity is from us. So the first value is always infinity. Okay, the rest of the values will change according to the data which you have. So this is where we have stopped, and we'll continue with the chi-square test and chi-square calculations in the next lecture as well.